Hello everyone, I am Yüsra Demirel and my group friends are Feridun Tavşanlı, Kevser Kahraman, Meryem Bürküt and Zeynep İnce. We had designed a Fenerbahçe Üniversitesi CPU RTL design and today I'm going to talk about this project. The purpose of this project is to develop the FP CPU, a processor that can execute 9 different operations. Various code snippets written in machine language will be written on the design processor. By the project's conclusion, it will be observed how the processor's registers, RAM, control units, and processing unit can work together and execute code snippets in machine language. And the system architecture. CPU has basically 4 elements. Those are register, memory unit, arithmetic logic unit, and control unit. The function of those units are RAM stores data for program execution, while registers manipulate data through flip-flop circuits. ALU performs arithmetic and logic operations, while CU decodes commands and sends data to ALU. And the tools used. Xilinx Vivado design suite uses Verilog and VHDL to generate a design file for FPGA. The FP CPU simulator visualizes the FP CPU architecture and helps observe data flow for text and software. Von Neumann architecture is used in FP CPU RTL design. And the design. There are 4 registers in the code. The state register indicates the current state of the state machine and control units. PC is a register that stores the microprocessor's next instruction address in memory. It holds the address of each instruction in memory. As commands are processed, the PC displays the next command's address. And we have IR. A register is temporarily storing upcoming microprocessor instructions. And we have ACC, aka accumulator. Register storing temp results of arithmetic and logical operations. The following table contains 9 supported CPU instructions. Those are load, store, add, subtract, multiply, jump, and jump if 0, no operation, and halt. The 10-bit FP CPU instructions bit separation is shown in the image below. The below graph displays the FP CPU state diagram outlining its task in detail. As you can see, there are state 0, state 1, state 2, state 3, and state 4. In state 0, the PC address is transferred to MAR to set the next memory access address. RAM write signal is set to 0, no memory write operation occurs. The state is incremented to transition to the next state, which facilitates the execution of the next instruction. The PC address is transferred to the MAR, and processor transitions to the next state, ready to read the next instruction. In state 1, MDR out is assigned to the IR, fetching and loading the instructions from memory. The PC is incremented by 1, preparing it for the next instruction, reflecting sequential execution in program memory. The state is incremented to prepare the processor for the next phase of the instruction execution cycle. State 1 fetches instruction from memory, loads them into the IR, increments the PC, and transitions to the next state for instruction execution. In state 2, the condition checks if IR 9 to 6 less than 6. If true, update MAR with IR 5 to 0 and transition to state 3. In this state, the processor performs memory read-write operations. If false, proceed to next condition. If IR 9 to 6 equal to 6, transition to state 0 for next instruction. The PC is updated with the lower 6 bits of IR, allowing for specific address jump. If IR 9 to 6 is 7 and ACC is 0, the program counter is updated with the lower 6 bits of IR, allowing for a specific address jump when ACC is 0. After that, transition to state 0 occurs. If IR 9 to 6 is equal to 8, transitions to states 0 occurs. If IR 9 to 6 is equal to 9, transition to states 4 occurs. 4. The processor readies itself to jump to a specific address upon meeting a condition. These conditions enable different control flows based on specific bits in IR, allowing specific command execution by the processor. In state 3, the state is set to 0, transitioning to the next instruction fetch. This completes the current execution cycle. The RAM write signal is set to 0, indicating no memory write operation. The memory address register is cleared to 0 as it is not needed. If IR 9 to 6 is equal to 0, MDR out is assigned to ACC, typically a load operation. If the top 4 bits of the instructions are 1, MIR is updated with the lower 6 bits. RAM write signal is set to 1 for a memory write operation. The ACC content is stored in memory at the MIR address. Usually this is a store operation. If instructions top 4 bits are 2, accumulator gets updated with current value plus MDR out. These operations execute arithmetic and data transfer instructions in processor dependent on the top 4 bits of the instruction. In state 4, nothing is checked or done, it's just spins on. Test case 1. This program loads values from memory, program performs arithmetic operations with the accumulator, and stores results back into memory using commands like load, add, and store. The program stops the processor after running. Memory address 50 and 51 store constants. And test case 2. Load the hexadecimal equivalent of the 5th to the 50 addresses in memory into the accumulator registers using the load command for FB-CPU. Multiply the value in the 50th address of the accumulator register with the expression's hexadecimal equivalent A at the address 51 using the mul command. The STO command recorded the value of the accumulator register in address 52. The test was stopped with the halt command. And test case 3. Load value 33 from memory address 51 into accumulator. Subtract value at address 49 from accumulator. Result is stored in accumulator. Hexadecimal representation is F1. Jump to addresses 10 is accumulator is 0. Load the value at addresses 48 into accumulator. Add the value at address 52 accumulator. Store accumulator value into memory address 48. Load value from memory address 49 into accumulator. The hexadecimal representation of this command is 31. Add the value from memory address 46 to accumulator. Hexadecimal AE. Store accumulator value into memory address 49. Jump to address 180. Load value from address 49 into accumulator. Store accumulator in memory address 52. Halt processor and program. Memory 46 is equal to 1. Memory 48 is equal to 0. Memory 49 is equal to 0. Memory 50 is equal to 5. Memory 51 is 10 in hexadecimal. As a result, test software 1, 2, and 3 were simulated in Vivado, enhancing our algorithmic thinking and Verilog language skills. Thanks for watching.